Hi there, how you doing? In this video we're going to be looking at a past HSC exam question and I'm going to walk through it with you step by step and explain all the concepts involved so you can answer it confidently. So the question that we're looking at is the 2009 HSC software exam, so last year's exam 2019. And it's question 32, and it involves, as you might guess, is a logic circuit. So in this video, I'm going to show you all the concepts related to logic gates so you can answer this question. So I'm going to assume that you know nothing about logic gates, or maybe you've learned a bit, but you're still not quite sure. So logic gates, so we're going to answer this question, but first I'm going to show you a bit of logic gates. So I recommend to all my students to go to this website called logic.li/demo, because it gives you all these fun little, it's like a drag and drop interface where you can drag these little icons and you can play around with logic gates yourself, and you can watch them happen in like real time. So look, I'll show you. So basically we have an input, and in this case we just have a switch. So the switch is on, off, and then we have an output, which is a light bulb. So if I click this and I drag it over here and connect the light bulb, I've made a wire connection. So if I do this, if I turn it on, the light bulb turns on, and if I turn it off, the light bulb turns off. So pretty straightforward. So now gets the good part. So I'm going to explain all the fundamental logic gates that you'll need for this course. So the most basic one is a OR gate. So the basic ones are the OR gate. So all you really need to worry about here is, so I have two inputs, so two switches, they go in here, and then I'm going to connect the output here. So the OR gate, let me zoom in here. Yeah, the OR gate, can I expand this? That might be a bit better. So the OR gate, that should be fine. So the OR gate looks like a little spaceship. It's like a little spaceship, and all this little spaceship does is if we put one of these switches on, it'll pass through the connection. So either that or that. So we'll turn the first one on, the light bulb goes on, we turn that switch off, we turn the second switch on, the light bulb also goes on. So it's called the OR gate, and as you can kind of guess, it basically means either of these inputs, like either the input say A or input B. If A or B are on, then the output, which we could call C, is on. So that's all it really is. It's pretty straightforward. So we'll get rid of this, and we'll go on to the next one called the AND gate. And the AND gate looks like looks like the forehead of Homer Simpson. It's like you could imagine there's a nose there and two eyes. Oh, I can't do it, but imagine it's like a like he's got the nose and he's got two eyes and he's like, yeah. So anyway, just think of it like that, and this is the AND gate, and all we think of is if we connect them both. So the AND gate's a little different from the OR gate in that you could probably guess that if one of these switches on, it will not activate, but if both of them are on, then the output will activate. So this is called the AND gate. Right. So I should also mention, I'll mention it later. So that's the AND gate. So pretty straightforward. So now we also have something called So those are the basic two like logic gates, and all the other logic gates are based off those two fundamental ones. So we have something called a NOR gate. So all the NOR gate is, turn the switches off. All the NOR gate is it's two input. It's like an OR gate, but it's inverted. So as you can see here, the light bulb is on. The light bulb is on. And I haven't even activated either of the switches. But if I activate either of these switches, then the light bulb will go off, as you can see. So it's simply an OR gate, but it's inverted. The output is inverted. So knowing that, this is a NAND gate. So it's like Homer Simpson, but he's wearing a little beanie and he's got a little beanie bob at the top. It's an AND gate, but it's inverted. So it's without any of the inputs, the switch is on, the light bulb is on, but if I turn one of them on, then it's still on, but if I put both of them on, then the light bulb will go off. So that's the NAND. So we're getting there. So there's one more, there's two more logic gates I need to work you through to show you, and then we can answer the HSC the question. So one of the trickier ones is called the XOR. I know these crazy names, XOR. So we had the NOR, we had the AND, the NAND, and now we have the XOR. Sounds like a Power Ranger, XOR. I've come to defeat you, Power Rangers, XOR. So we have the XOR gate. And the XOR gate's kind of like the OR gate. So if we put one of these on, the light bulb will go on. But this is the difference. If we put both of these switches on, then the light bulb is not off. It is off. Sorry. So basically, when you think of XOR, think of the X. The X represents is shorthand for exclusive. So it basically means it's exclusive OR. So only one of these switches can be on to pass it through. If both of them are on, then the light bulb goes off. The complement to this is the XNOR. So it's the X and the N. So if you can probably guess what that is, it's an XOR. It's a XOR, but it's inverted. So if none of them are on, it's on. If one of them are on, it's off. But if both of them are on, then it's also on. So it's just an inverted XOR. So, as I said, if this is confusing, go to logic.li/demo, and I highly recommend you play around with this yourself, just so you can get your head around it and you can make more complicated circuits. So, so the last thing you need to know is there's this thing called a buffer, which is just a triangle, and you don't really need to worry about too much because it just passes the signal along. If you study like electrical engineering, buffers become more important, but this is just programming, so you just have to think the triangle does nothing. Don't really worry about it. But if you see a triangle with a little dot, a little circle at the end, this is actually really important because all that does is invert the signal. So anytime you see the little dot at the end of an object, it usually means it's an inverter. That's the key to seeing inversions. So inversion, it's off, the light bulb's on. If the switch is on, the light bulb is off. Right. So that's all you really need to know. Those are all the really basic logic gates, and I think that's all you really need for this course. So let's, using that knowledge, let's answer this question from the exam. Right, so it says consider the following logic circuit, and oh boy, it looks kind of complicated. Like, I don't know what's going on. There's like 4. So I've just shown you like one logic gate at a time, but whoa, there's like 4 logic gates. 5 logic gates right here, and it's like, it's a bit confusing, isn't it? But don't worry, we're going to break it down. So draw a circuit that is logically equivalent to the circuit provided, but which uses the fewest number of gates possible. So basically we need to look at this circuit, look at this, and simplify it. And then it says support. So the key to this question as well is support your answer with the relevant truth table. And that's like a little hint for you about how to solve this question, because most people, most students, if you're looking at this, might get a bit overwhelmed. But if you're ever overwhelmed, always look to the question, because there will be a little hint to help you. And in this case, it's this little line here. So you might be asking, well, okay, what is a truth table, and how is it going to help me solve whatever this is? Like, how am I going to do it? I'll show you right now. So basically, a truth table is similar to a desk check if you've done that. And all you have to do for the truth table is this. So as you can see here, instead of switches, like, oh, that is way too big. So we had like, on logic.li, we had these switches, and then we had like a light bulb at the end. You know, please forgive my terrible drawing. I'm a programmer. I'm not an artist here, so forgive me. So in logic.li, we had like these switches, and you turn them on, and then the light bulb like goes on. In the exam and other places, you won't obviously, the switches and the light bulb is simply a convenience, like it's to help you understand what's going on. But in the exam, you won't have that. Instead, they'll give you these letters. So in this case, A and B. So the other thing to remember, which I forgot to tell you, is always go from left to right. So the inputs are on the left and the output is on the right. So in this case, A and B are inputs. They're like the switches we had, and Z is the final output. But then you're all probably asking me like, oh, look, why is there V, W, Y, and X? So you can think of V, Y, W, X as just like little points of interest that we might want to know the value of. You could think of them as like little light bulbs. So they're like also little light bulbs if we're using the metaphor of a light bulb. And they're either off or on, right? So using all these like letters, we can basically break it down in like a table. And basically to do that, all you do is this. So you write the letters. So A, B, V, W, X, Y, Z. And then we draw a table. So we draw a line. We draw a line here, we draw a line there, we draw a line here, so on and so forth. So this is what you do in the exam, by the way, because they give you plenty of space. So you draw all this, and basically we want to fill this table out. So with inputs, so remember how we had our switches? The switches can only, our input switches can only take two values, either off or on. So basically we need to fill out these two columns, A and B, with all the potential possible inputs. So in that case, let's say both A and B, the switches are off. Let's say A was off, B was on. Let's say A was on and B was off. And let's say both A and B were on. Right. So now all we've got to do is basically look to these values and fill out our table. So as we can see here, if let's say both A and B are off, so let's inspect to see what V would be. So A comes out here, and then we have that little triangle with the little circles, so we know that that is an inverter. So the 0 becomes a 1, so then we know V at this point, because there's no other input to V, the only input to V is A after it's been inverted by this triangle, so we know that V has to be 1. So as you can see here, V is 1. Okay, so let's check out W. So W is the same thing, so B. So just to explain, these, like, see these black dots on this diagram? You're probably wondering, well, you didn't show me that, Locke. What are they? And you're freaking out. Don't worry. These dots are simply telling you that the connection is split into two. So there's like a connection going in from B, and then it splits onto two paths. So as you can see for A, for example, A, the signal's coming down here, it goes straight ahead, but then it splits off down here as well. So A will split off to there, and B will go straight ahead, and then it'll also split off here. So that's what you just got to keep in mind. So, I'll just keep that on. I've done that before. So, for W, we can see the only input to W is the inverted B. So B is 0, so obviously W is 1. Alright, so far so good. So let's look at X. So the X input is the weird spaceship. So when we see the spaceship, we think, I know what that is. Locke taught me. It's an OR gate, because it's the spaceship. The inputs to X are V and B. So only one, either V or B has to be true. So we know V is true, so then X has to be true or on, if you will. Because V is 1, so it's passing through the OR gate, and the OR gate then says, oh yeah, we've got one of my inputs is on, so let's pass the output as on, so X is on. So similarly for W, W down here, we know that W is on, so it passes through the OR gate, so we know that W would be on. So far so good. So then we look at Z and we see the little Homer Simpson logic gate here, so we know, that's the AND gate. So we need both X and Y to be on for the AND gate to say that Z is true. So we know that Z and Y are 1, so we know the AND works, so then we know Z is on. There we go. Oh, I'm drinking some peppermint tea on this cold day. It's quite refreshing. I should mute the mic. I should not be like drinking and have the mic active. My apologies. Alright. So with the next one, we have A is 0 and B is 1. So let's start simple. Let's say, okay, if V, what is V? So if A is off, we know that V would be on, so that's simple. Now W, if B is on, then the signal would get inverted, so that means W would actually be off. Because the signal's inverted, remember, so it would be off. So then let's go to X. So X, we know that V is on, so we don't even have to look at the other input. If V is on, then we know that X is on as well. So too easy. So now we look at Y. So we know that W is off, so then this forces us to look at the other input. And the other input is A. And we know A is off, so therefore Y would be off as well. So as you see, W is off. We've already determine that, and we look at the other input, which is A, and we know A is off, so that means Y is off. And if Y is off, then the AND gate will fail and Z will end up being 0 as well, because only if X and Y are true or on, that the Z would be true as well, or on. Alright, halfway done, we're nearly there. So now what if A is 1 and B is off? So let's see V, so we know V is inverted, so V must be 0 if A is on. W would be true, and then X would be, so V is off, and then we know B is off, so then X would be off, and we know Y would be, I would be on because W is on, and then we know Z would be 0. So we're getting closer. So finally, if both A and B are on, so what would V be? V would be inverted, so V would be 0. W would be inverted B, so that would be 0. X, so here's the trick. So X, we know V is 0, but if we look at the other input, we know B is on. And remember how the B kind of splits off and goes down into the input of the other OR gate up here for X? So then that would mean that X would also be true because B is true. If we look at Y, it's basically the same. Since A is true, then Y would also be true because A is passing a signal all the way down into this OR gate as well. So both x and y in this case would be true, and therefore z would be true. Alright, so that's the table completed. It's a little involved. The question's a little involved, but hopefully you've stayed with me. If you're confused about anything, just go back, rewind through the video, and just go over it again, I think. So, you've done your truth table. We've got this far. So how do we finally draw the logical equivalent of this circuit? So I'll give you a little tip. So how we do this, how you simplify a circuit. So if you've drawn this in the exam, don't do what I'm about to do, but this is just an exercise to help you, is I want you to only look, this is how you simplify the circuit. We need to only look at the inputs and the output. So I'm just going to blank out this for a second. We're going to blank out the middle. So we're just going to blank it out. For a hot second. So we're going to blank it out. And as you can see here, all we have left is A and B, the inputs, and Z, the output. And we just want to inspect that and see, okay, what logic gate or gates will be equivalent to this. So let's look. So if A and B are off, then Z is 1. If either A or B are on, then Z is off. And if both A and B are on, then Z is on. So I want you to take a moment and think about what you think the output would be here. And the answer to that is, if we go back here, what of our gates do we need to create that? So it's like an OR gate. So if you picked up that it is the XNOR gate, you are correct. Because if we go back here, if both of the inputs are off, then we have a 1 value. If one of the inputs is on, then the output is off. But if both of them are off, both of them are on, sorry, then it's also on. So the answer to this question is a XNOR gate. So it's kind of one of the more funky ones, but you've got to be perceptive to realize, got to remember what those gates, their inputs and outputs look like, and identify what they are. So yeah, so it is the XNOR gate. So whenever you see this, your best bet, your instinct when you see the inputs and the outputs might be to think, okay, I just need to start drawing circuits, right? I might need to maybe it's like A and this is B, and then I have to draw maybe a NOR gate, and then I have to draw another gate somewhere else. So before you start creating this complicated circuit, which may be like, oh, this is like 5 gates, so maybe I can create a circuit with 3 gates, always, I think, double check all your basic gates. So go through like the OR gate, the AND gate, the ZAND gate, the XOR gate, the XOR gate, and then the XNOR gate. Go through all those and see if it matches up. And if it does, then hallelujah, then you can just draw that. If it doesn't, then you have to basically try and use like 2 or 3 gates to make something simpler. As you see here, they give you space to like write stuff, and then they give you this like space to draw a diagram. So you'd want to draw the logic gate diagram in here. In this case, the XNOR. Just draw. You'd want to draw A, B. Oh God, that's horrible. So you draw like A,
B is inputs, and you draw Z over here. And then remember to draw the XNOR. So you start with your spaceship for the XNOR is just like an OR gate but modified. So you start with the OR gate, and then you draw your little beanie bob. And then for the XOR, all you have to do is draw like a line out here like this. And then I think you keep drawing the line. So it's like a exclusive. You have to draw the extra line there to make sure, and then you draw the line to the output. So that's all you'd need to draw. And you can even say, you can write down here XNOR if you want. If your drawing's as bad as mine, you can just write XNOR down there, just to make sure the marker knows what you're talking about. So, yep. All right. Thanks for tuning in. So that's pretty much the logic gates. I'll do more in the future. So, all good. If you're interested in my tutoring and software design and development, check out my website, links down below. Thanks. Bye-bye now.